Okay, now let's try and solve this problem by calculus. We know that the total magnetic field, in this case just the Z component, is equal to the sum of all the little dBs, the little bits of magnetic field from all the little bits of wire. So you can write that in full as the sum of all the little bits as Y varies from the bottom of the rod to the top of the rod, and the step equation we worked out before from the Biot-Savart law. Now, we'll do the usual calculus trick, and that is approximate. But if we make these y steps very, very small and get very, very large numbers of them to compensate, then it gets more and more accurate. And as we take the limit, as the delta y's tend to 0, so as our slices become infinitesimally small and the number of them becomes infinitely large, this becomes accurate. So b is equal to the limit as delta y tends to 0 of the sum of the delta b's, and that, as usual, means the sum turns into an integral. So we've got an integral from minus L over 2 to L over 2, so a definite integral, mu naught over 4 pi I x over x squared plus y squared to the 3 halves, and the delta y turns into a dy. Okay, so if we get that integral, it'll tell us our answer. It's a very tricky integral, but as usual it can be done by looking it up in standard tables of integrals or by Wolfram Alpha or Mathematica or something similar. And it turns out that it comes out as, let's bring the constants outside, mu naught I x over 4 pi. The integral is y over x squared root x squared plus y squared, still over the range from the top to the bottom. It's minus L over 2. And if we plug in numbers and simplify down, that comes out as mu naught over 4 pi L times I all over x root x squared plus L over 2 squared. So that's our analytic solution. Let's test it, check it. One way to check it is to put in numbers, and we'll find we'll get very much the same answer as our numerical estimate, so that's a good sign. We can check limiting cases. We know that from the Ampere equation that if it was infinitely long, we'd have b equals mu naught over 4 pi times 2i over x. And if we see here, if we make L very much bigger than x, so an infinitely long wire, then we can ignore this term down there. This one dominates. So square root of L over 2 squared is just L over 2. 2 goes on the top. L's cancel, and indeed you get this. So it has the right limiting case when L is very much bigger than x. We can also check units. We know the dimensions of this are correct, and this one's got the same constant. It's got the I on the top, and it's got an x on the bottom, and an L over root length squared. So root length squared is going to be length. Length of length cancels out. So the dimensions of this and this are the same. So it all seems to work. So this looks plausible.